For thousands of years, we have gazed up at the stars and asked one of humanity's most profound questions. Are we alone in this universe? That cosmic curiosity is no longer just a philosophical wonder. Right now, we are living through an unprecedented revolution in our search for answers, thanks to discoveries that are reshaping everything we thought we knew about where life might exist. Imagine for a moment worlds with not one but two suns in their sky, planets drenched in eternal twilight, or oceans hidden beneath miles of ice, warmed by the gravitational pull of a distant gas giant. These aren't scenes from science fiction. They are real places orbiting distant stars, and each one challenges our very definition of what makes a world habitable. Just a few decades ago, we knew of no planets beyond our own solar system. Today, thanks to missions like Kepler and TESS, we've confirmed over 5,000 exoplanets, and among them are strange, beautiful, and utterly unexpected environments where life might just find a way. The classical idea of a habitable zone, that narrow band around a star where water could flow liquid on a planet's surface, has expanded into something far more dynamic and thrilling. We now understand that life could thrive in places we once thought were utterly hostile. In the deep, dark oceans of icy moons, in the thick atmospheres of super-Earths, or even on tidally locked planets where one side is perpetual day and the other eternal night. This video is an invitation to journey with us to 25 of the most promising alien worlds that could harbor life. We'll explore swirling storms on distant gas giants, peer beneath the ice of frozen moons, and even visit planets where it might rain glass sideways in howling winds. Each of these worlds tells a story not just about the possibilities of life beyond Earth, but about our own place in the cosmos. You're about to witness places that defy imagination, where the rules of nature are rewritten, and where the dream of finding another living world feels closer than ever before. So settle in, look up, and let's explore the frontiers of discovery together. Our journey begins not in some far-flung corner of the galaxy, but right on our cosmic doorstep. Just 4.2 light-years away, orbiting the star closest to our own sun, is a world that has captivated astronomers and dreamers alike, Proxima-Centauri-b. Despite its immense distance in human terms in the vast scale of the universe, this planet is practically our next-door neighbor. What makes this world so extraordinary is its mass, which is remarkably similar to Earth's, suggesting a rocky composition we would instantly recognize. But its true allure lies in its position, nestled within the habitable zone of its parent star, Proxima Centauri. This is that tantalizing region where temperatures could be just right for liquid water to exist on the surface, the ingredient we consider most essential for life as we know it. However, this potential paradise comes with a set of extreme challenges that paint a far more complex picture. Proxima Centauri is a red dwarf star, a type of star known for its ferocious and unpredictable nature. It frequently unleashes devastating stellar flares, eruptions of radiation that could bombard the planet's surface, potentially stripping away any atmosphere and scouring the landscape of any nascent life forms. Furthermore, because the planet orbits so close to its dim star to stay warm, completing a full year in just 11 Earth days, it is almost certainly tidally locked. This means one side of the planet is perpetually bathed in daylight, while the other is frozen in an eternal, starless night. You might picture a world of stark contrasts, a scorching hot dayside and a brutally cold nightside, with perhaps a narrow, temperate twilight ring in between where conditions could be just survivable. Yet, against these odds, scientists remain profoundly hopeful about Proxima Centauri-b's possibilities. Why? Because life on Earth has proven to be incredibly resilient, thriving in the most unexpected and hostile environments, from deep-sea volcanic vents to acidic hot springs. If an atmosphere exists, it could potentially redistribute heat around the planet, mitigating the extreme temperature differences. Liquid water might persist in subsurface oceans, shielded from the stellar fury above. This world forces us to broaden our imagination, to consider that life, if it is there, may not look like anything we've seen before, hunkered down in cryptic niches and defying the harshness of its home. Proxima-Centauri-b stands as a powerful symbol, a reminder that the search for life isn't always about finding another Earth, but about discovering all the strange and wonderful ways a living world might actually work. Leaving our closest stellar neighbor behind, we venture next to a planetary system that redefines the very idea of a solar family. 39 light-years from Earth lies the TRAPPIST-1 system, and orbiting its faint, ultra-cool dwarf star is a world that has become one of the most coveted prizes in the search for life, TRAPPIST-1e. This isn't just another exoplanet, it's a key piece in a stunning cosmic puzzle, a system so packed with promise that it has astronomers around the world utterly fascinated. What makes this world so special starts with its size. It is almost exactly the same radius as Earth, making it a true rocky twin in terms of its physical dimensions. But its true appeal lies in its location, sitting perfectly within the star's habitable zone. This is the Goldilocks position, where the energy from the star could allow for liquid water to flow, pool, and persist on the surface. The environment of TRAPPIST-1e is shaped by its quiet, cool star. Unlike our turbulent sun, this dwarf star emits a gentle, reddish glow, creating a perpetual twilight across the landscape. A year on this world passes in a blur of just 6 Earth days, a testament to its incredibly close orbit. If you were standing on the surface of TRAPPIST-1e, the star would appear 3 times larger in the sky than our sun does, casting a dim, salmon-colored light across a world that might feel strangely familiar. The potential for a temperate climate and vast oceans makes it a primary candidate in the search for a biosphere beyond our solar system. However, this proximity also raises questions. The planet is likely tidally locked, meaning one hemisphere is in constant daylight while the other is locked in an endless cold night. Yet, models suggest that a thick enough atmosphere could efficiently transport heat around the globe, potentially creating a band of habitable territory along the terminator line, the border between light and dark. Perhaps the most breathtaking aspect of TRAPPIST-1e is not just the planet itself, but the extraordinary system it calls home. It is one of 7 known Earth-sized planets orbiting the same star, a family of worlds all remarkably similar in size to our own. This compact system is a celestial dance of gravitational harmony, with the orbits of these 7 worlds packed into a space smaller than the distance between our Sun and Mercury. From the surface of TRAPPIST-1e, the other planets would not be mere points of light. They would appear as magnificent orbs, some larger than our moon, dominating the sky in a silent, majestic procession. This unique configuration offers an unprecedented opportunity for science. Because the planets transit so frequently in front of their star from our viewpoint, we can study their atmospheres with unparalleled precision. This is where our greatest tool comes into play, the James Webb Space Telescope. Its powerful infrared eyes are perfectly suited to analyze the starlight filtering through the air of TRAPPIST-1e, searching for the chemical fingerprints of life or biosignatures. Scientists are actively looking for traces of gases like oxygen, methane, or carbon dioxide in specific combinations that would be difficult to explain without biological processes. The discovery of an atmosphere around TRAPPIST-1e would be a monumental step forward, and every observation brings us closer to understanding the true nature of this captivating world. It represents a whole new paradigm for habitability, a system where multiple Earth-sized worlds exist in a single stellar backyard, each offering a unique environment where life could have taken hold. Moving further into the cosmos, we encounter a world that holds a special place in the history of exoplanet science. Kepler-186f, discovered in 2014 by the venerable Kepler Space Telescope, this planet wasn't just another entry in the catalogue, it was a landmark revelation. Kepler-186f earned the profound distinction of being the very first validated Earth-sized planet ever found orbiting comfortably within the habitable zone of another star. Before its discovery, we knew of larger planets in that sweet spot, so-called super-Earths, but finding a world that so closely mirrored our own in size, positioned where liquid water could exist, was a game-changing moment. It was the first tangible evidence that planets like ours, with the potential ingredients for life, were not just theoretical possibilities but actual realities in the Milky Way. This pioneering world lies about 500 light-years away from us in the constellation Cygnus. It orbits Kepler-186, a red dwarf star that is smaller, cooler, and redder than our Sun. The planet completes a full orbit every 130 Earth days, placing it near the outer edge of its star's habitable zone. Because the star itself is so much dimmer than our Sun, the energy reaching Kepler-186f is comparably meek. The brightness at high noon on this world would be similar to the light we see on Earth just about an hour before sunset. You would live your life in a perpetual, dim, reddish glow, a starkly different experience from our sun-drenched reality. Its Earth-like size is the core of its significance. With a radius just 10% larger than Earth's, astronomers are highly confident that Kepler-186f is a rocky world, much like our own, as opposed to a gaseous mini-Neptune. This rocky composition is a critical prerequisite for life as we understand it, providing a solid surface, potential for plate tectonics to regulate climate, and the right conditions for chemistry to unfold. However, many questions about its true nature remain open. We don't yet know if it possesses a protective magnetic field to shield itself from stellar radiation, or if it has managed to hold onto a life-sustaining atmosphere over billions of years. What truly cemented Kepler-186f's legacy was the door it kicked open. Its discovery was a powerful proof of concept, demonstrating conclusively that Earth-sized worlds in habitable zones were out there waiting to be found. It shifted the search from if such planets existed to how many there were, galvanizing new missions and refining our search strategies. This single world expanded our horizons and fueled the optimistic belief that somewhere out there, another Earth, not just in size but in essence, might be circling a distant star waiting for us to find it. While Kepler-186f was a milestone for its size, our next destination represents a world that some scientists argue could be an even better cradle for life than our own. Meet Kepler-442b, a super-Earth orbiting in the habitable zone of a star over 1,100 light-years away. This planet stands out not just for being promising, but for ranking exceptionally high on the Earth Similarity Index, a scale scientists use to gauge how closely an exoplanet's conditions mirror our own. With a radius approximately 1.3 times that of Earth, it falls into a fascinating category of worlds known as super-Earths, planets larger than ours but smaller than ice giants like Neptune. This size is particularly intriguing because it suggests Kepler-442b is almost certainly a rocky world, but with a stronger surface gravity that could help it hold onto a life-sustaining atmosphere for billions of years. What truly sets this world apart is its sun. Kepler-442b orbits a K-type star, often called an orange dwarf. These stars strike what many astrobiologists consider a Goldilocks balance between the turbulent fury of smaller red dwarfs and the relatively rapid burnout of stars like our Sun. Our own G-type star, while nurturing, has a lifespan of roughly 10 billion years, and its luminosity has been steadily increasing over time, a trend that will eventually render Earth uninhabitable. A K-type star, however, is smaller, cooler, and more stable. It burns its nuclear fuel far more slowly, boasting a potential lifespan of 20 to 70 billion years. This extraordinary stability offers a cosmic gift: time. It provides an almost unimaginably long, steady window for life to emerge, evolve, and potentially thrive on any orbiting planets. This brings us to the most compelling argument some researchers make that Kepler 442b might actually be more habitable than Earth. The key lies in the amount of energy it receives from its star, a value astronomers call stellar flux. Based on current data, it's estimated that Kepler 442b receives about 70% of the stellar energy that Earth gets from the Sun. While that might sound dim, it is likely more than enough to maintain liquid water, especially if the planet has a greenhouse atmosphere similar to our own. Crucially, this level of energy receipt is seen by some models as being in a sweet spot for efficient photosynthesis. On Earth, plants use specific wavelengths of light most effectively. The light from this K-type star, richer in the red and infrared wavelengths that photosynthesis often favors, could potentially provide an even more ideal energy source for any plant-like organisms that might evolve there. Imagine a world where the sun in the sky is a deep orange orb, casting a warm, perpetual sunset hue across landscapes that could be lusher and more vibrant than our own tropics. The longer lifespan of its star means this world isn't racing against a celestial clock. It has been, and will remain, a stable environment for epochs longer than our entire solar system has existed. While we still don't know if Kepler 442b has an atmosphere or a magnetic field, its placement around such a stable star and its position in the habitable zone make it a prime candidate for everything we believe is necessary for a living world. It challenges our Earth-centric view of habitability, suggesting that the perfect home for life might not be a twin of our own planet, but a slightly larger, slightly different world orbiting a quieter, more enduring sun. For our fifth world, we travel 49 light-years to a system that has quickly become one of the most thrilling in the entire exoplanet catalog, LHS 1140b. Picture a planet so massive that it dwarfs our own, a true super-Earth with a mass nearly 6 times greater than our home world. Despite its formidable size, what truly captivates scientists is its composition. This is overwhelmingly likely a rocky world, a colossal terrestrial planet that might possess a landscape of vast mountains and deep canyons on a scale we can scarcely imagine. It resides in the habitable zone of its quiet red dwarf star, a region where temperatures could allow for the magic of liquid water to exist. But what sets LHS 1140b apart from the countless other exoplanets we've found is its status as a prime, almost perfect laboratory for the next generation of astronomy. The story of its discovery is a testament to the precision of modern science. Unlike many worlds found by the transit method, where astronomers watch for a star's light to dim as a planet passes in front of it, LHS 1140b was detected using the radial velocity technique. This method involves watching the star itself, detecting the subtle wobble induced by the gravitational tug of an orbiting planet. It's like listening to the universe's quietest symphony, hearing the faint note of a planet's gravity in the motion of its star. This discovery method immediately gave scientists a crucial piece of information: the planet's mass. Combined with later observations that determined its size, they were able to calculate its density, which pointed irresistibly to a rocky, metal-rich world, perhaps with a massive iron core. Now, the most exciting possibilities come into view. A planet of this density and mass, located in the habitable zone, has a tremendous advantage in the search for life. It likely has the gravity necessary to hold onto a substantial atmosphere. While many planets around red dwarfs are vulnerable to having their atmospheres stripped away by stellar flares, LHS 1140b's stronger gravitational pull acts like a shield, potentially keeping a thick blanket of air securely in place for billions of years. This is the first ingredient for a habitable environment. The second, and even more tantalizing possibility is that this world could be a massive water world. Some leading models suggest that a significant portion of its mass could be water, likely in the form of a global, planet-wide ocean. Envision an entire planet with no land in sight, a dark, deep abyssal world covered by a single, endless sea, potentially dozens of times deeper than our own Mariana Trench. The characteristics that make LHS 1140b so promising for life also make it exceptionally promising for our studies. Its parent star is a calm, old red dwarf, notably quiet and stable compared to its volatile cousins like Proxima-Centauri. This means the planet is less likely to be bombarded by radiation that could fry its surface or erode its atmosphere. Furthermore, from our vantage point on Earth, LHS 1140b transits directly across the face of its star. This geometric luck is a gift to astronomers as it allows us to use the most powerful tool at our disposal, spectroscopy. When the planet transits, starlight filters through its atmosphere if it has one. By analyzing that filtered light with instruments like the James Webb Space Telescope, we can dissect it into a spectrum, reading the chemical fingerprints of the gases present. Scientists are poised to search for the telltale signs of a living world, the combination of gases like oxygen and methane that, when found together, are difficult to explain through geology alone and often point to biological activity. The combination of its likely rocky nature, its potential thick atmosphere and ocean, and its perfect alignment for observation makes LHS 1140b not just another interesting exoplanet, but arguably one of the single most important targets in the entire sky for the search for life beyond Earth. It represents a new era where we are moving from simply discovering planets to truly characterizing them, peeling back their atmospheric layers from light years away to answer the ancient question of whether we are alone. Just 12 light-years from Earth, a cosmic whisper holds a secret that has sent ripples of excitement through the scientific community. Teegardens-star, a faint, ancient red dwarf so dim it wasn't even discovered until 2003, is home to not one, but two of the most intriguing Earth mass planets ever found. Named Teegardens-star B and C, these worlds are a powerful double offering in our search for life, a tandem discovery that makes this nearby system one of the most compelling targets for astrobiologists everywhere. What makes them so extraordinary begins with their pedigree. Both planets have minimum masses almost identical to Earth's, strongly suggesting they are rocky, terrestrial worlds just like our own, rather than gaseous mini-Neptunes. This alone would be cause for celebration, but their location elevates them to another level entirely. Astoundingly, both of these Earth-like worlds orbit within their star's calculated habitable zone. This is the region where temperatures should be just right for liquid water to exist on a planetary surface. Teegardens-b, the inner planet, is considered highly optimistic in this regard, receiving a similar amount of stellar energy as Earth does from our Sun. Teegardens-c, orbiting a bit further out, sits in a more conservative, cooler region of the habitable zone, perhaps more analogous to Mars in our own system, but still well within the realm of possibility for hosting liquid water, especially if it possesses a greenhouse atmosphere to trap heat. Finding one such planet is a remarkable stroke of luck. Finding two in the same system, both potentially habitable, feels like winning the cosmic lottery. The allure of this system is deepened profoundly by its incredible age. Teegardens-star is a cosmic elder, estimated to be around 8 billion years old. That is nearly twice the age of our own solar system. To grasp the immensity of that timescale, consider that when our Sun and Earth were first forming from a swirling cloud of gas and dust, the Teegardens-star system had already been a stable, mature planetary family for over 3 billion years. This vast expanse of time is the most valuable commodity for life. It provides an almost unimaginable window for the slow, intricate dance of chemistry to evolve into biology, and for that biology to grow in complexity and resilience. On Earth, it took roughly 1 billion years for the first simple life forms to emerge. The Teegardens planets have had 8 times that long for life to not only begin but potentially to flourish, adapt, and perhaps even intelligence to develop. This is the core reason why the discovery of these twin worlds is so electrifying. Astrobiologists aren't just looking at two potential abodes for life. They are looking at two potential abodes for life that have had an eternity to experiment with evolution. The possibility exists for not just one, but two separate biospheres to have arisen in the same stellar neighborhood, perhaps even allowing for the exchange of material between them via meteorites, a process known as panspermia. Furthermore, the star itself is exceptionally quiet and stable for a red dwarf, showing little of the violent flaring activity that plagues stars like Proxima-Centauri. This calmness greatly increases the chances that both planets could have held onto their atmospheres over these billions of years, preserving any potential life from being scorched away by stellar tantrums. The Teegardens-star system presents us with a breathtaking scenario, a nearby, ancient and tranquil solar system with two shots at finding another living world, each one a time capsule from an era long before our own sun even ignited. Now we venture into the realm of the truly exotic, to a world that defies our traditional search for another Earth and opens up a breathtaking new category of potentially habitable planets. Located 120 light-years away in the constellation Leo, K2-18b is a sub-Neptune, a type of world entirely absent from our own solar system. It is far larger than Earth but significantly smaller than Neptune, occupying a mysterious middle ground that has forced astronomers to completely rewrite the rules of the habitability game. The initial discovery of this planet was fascinating, but what happened next sent shockwaves through the scientific community and made international headlines. When the James Webb Space Telescope and its predecessor, Hubble, turned their gaze toward K2-18b, they detected the unmistakable spectral signature of water vapor in its atmosphere. This was a monumental achievement, marking one of the first times we had directly identified water, the universal solvent for life as we know it, in the atmosphere of a planet in the habitable zone. But K2-18b is no twin of Earth. Its size and composition are something far stranger and more wondrous. This planet is over 8 times more massive than Earth with a radius 2.5 times larger. Such a world could not have a rocky surface like our own. The physics simply doesn't allow it. Instead, scientists believe it is what they call a Hycean world, a portmanteau of hydrogen and ocean. Picture a planet with a massive primordial atmosphere dominated by hydrogen, a thick and hazy envelope that extends deep into the planet's interior. Beneath this immense atmospheric pressure at a certain depth, conditions might become just right for something miraculous to occur, a planet-wide ocean. Not an ocean resting on a rocky seafloor like ours, but a global, supercritical water layer, perhaps hundreds of miles deep, that constitutes the very body of the planet itself. It would be a world without land, a dark, boundless aquatic abyss under a crushing, opaque, pinkish atmosphere. The concept of Hycean planets is revolutionary because it shatters the Earth-centric model of habitability. We once focused almost exclusively on finding rocky planets of a similar size to our own. K2-18b and worlds like it proclaim that life could potentially thrive in environments we once considered utterly hostile. The habitable zone for a Hycean world is actually much wider than for a rocky planet, because the thick hydrogen atmosphere creates a powerful greenhouse effect, trapping heat efficiently. Such a planet could orbit much further from its star and still maintain warm enough temperatures for a liquid water ocean to exist deep below the clouds. Conversely, it could also orbit closer in, as its ocean would be protected from evaporation by the immense atmospheric pressure above it. This dramatically expands the number of possible abodes for life in our galaxy. The detection of water vapor was just the beginning. The same observations also hinted at the presence of dimethyl sulfide, or DMS. On Earth, DMS is a gas produced almost exclusively as a byproduct of biological activity, primarily by marine phytoplankton. Its potential detection in the atmosphere of a water world is, to put it mildly, incredibly provocative. It is exactly the kind of biosignature scientists dream of finding. However, this initial data is not yet conclusive. The signal is faint and requires further, more precise observations to confirm. This is where the future gets so exciting. K2-18b is now one of the most heavily scrutinized exoplanets in the sky. The James Webb Space Telescope will continue to stare at this world during its transits, gathering more light to build a higher fidelity spectrum of its atmosphere. Scientists will be searching not only to confirm the presence of DMS, but also for other potential biomarkers like methane and ozone. K2-18b has become a living laboratory, a test case for an entirely new astrobiological paradigm. It forces us to ask not just if we are alone, but what form life might take in the universe's most unexpected corners. Our journey now takes us 31 light-years away to a compact, fascinating system that challenges our assumptions about where life might take root. Orbiting the star GJ357 is a trio of planets, but one stands out as a world of profound mystery and potential: GJ357d. This super-Earth is a compelling enigma, a planet that forces us to reconsider the very fundamentals of the habitable zone. It receives approximately the same amount of stellar energy from its dim red dwarf sun as Mars does from our own. At first glance, that fact would seem to relegate it to the category of a frozen, lifeless world. Yet GJ357d is officially categorized as orbiting within its star's conservative habitable zone. How can this be? The answer lies not in the amount of energy, but in what the planet itself might be made of. If GJ357d is a dense, rocky super-Earth with a solid surface, its prospects for habitability hinge entirely on the presence of a sufficiently thick atmosphere. A robust atmosphere rich in greenhouse gases like carbon dioxide or methane could act as an incredibly effective insulating blanket. This greenhouse effect would trap the meager heat from the star, potentially raising surface temperatures high enough to allow for pockets of liquid water to exist, perhaps in subsurface reservoirs or in equatorial regions. In this scenario, GJ357d could be a cold, but not terminally frozen world, a place where life could persist in sheltered environments, much like the extremophiles found in Antarctica's dry valleys on Earth. However, a second, equally plausible hypothesis paints a very different picture. Based on its mass, at least 6 times that of Earth, many planetary scientists argue that GJ357d is more likely to be a mini-Neptune than a super-Earth. This distinction is everything. A mini-Neptune would lack a solid surface altogether. Instead, it would possess a relatively small rocky core enveloped by a massive, deep atmosphere of hydrogen and helium, extending thousands of miles into space. In the crushing pressures and profound depths of such an atmosphere, the concept of a liquid water ocean as we know it becomes irrelevant. Any water would be a superheated, supercritical fluid, and the chances of life as we understand it existing there are considered vanishingly slim. This ongoing debate is the central drama of GJ357d. It is a celestial Rorschach test where scientists see either a cold, rocky world with a fighting chance or a gaseous dwarf with none. What adds an extra layer of fascination to this system is the company this world keeps. GJ357d is not alone. It shares its star with 2 other confirmed planets, GJ357b and c. The innermost planet, GJ357b, is a hot, rocky world dubbed a hot Earth, whipping around its star every 3.9 days. GJ357c is a warm, sub-Neptune-sized planet orbiting every 9 days. This compact architecture, with 3 diverse worlds orbiting closer to their star than Mercury does to our Sun, is a classic feature of red dwarf systems. It offers a fantastic natural laboratory to compare and contrast planetary formation and evolution under similar stellar conditions. The presence of these siblings makes the GJ 357 system a rich target for study, as understanding the nature of the inner planets can help us constrain the possible characteristics of the mysterious outer sibling. The resolution of GJ 357D's true nature lies in the future of atmospheric characterization. The key will be to determine if it transits or passes in front of its star from our vantage point on Earth. A transit would allow astronomers to use the James Webb Space Telescope to perform transmission spectroscopy, analyzing the starlight that filters through the planet's atmosphere to decipher its chemical composition. Finding signs of hydrogen would strongly support the mini-Neptune model, while detecting heavier gases like carbon dioxide or nitrogen would point toward a rocky world with a secondary atmosphere. Until that crucial geometric alignment is confirmed, GJ 357D remains a beautiful puzzle, a world that embodies the current frontier of exoplanet science, where a single measurement can completely redefine a planet's potential from a barren rock to a gaseous giant, and where the habitable zone is not a simple line but a complex conversation between a star's light and a world's composition. Turning our gaze to a discovery that heralded a new chapter in planet hunting, we arrive at TOI 700D, a world that stands as a landmark achievement for one of NASA's most prolific explorers. This Earth-sized planet, orbiting comfortably within its star's habitable zone, earned the historic distinction of being the very first such world discovered by the Transiting Exoplanet Survey Satellite, or TESS. Launched in 2018, TESS was designed with a singular, ambitious goal: to scan nearly the entire sky, monitoring the brightest stars closest to our Sun for the telltale dips in light that signal an orbiting planet. TOI 700D was the mission's monumental proof of concept, a resounding announcement that TESS was not only operational but capable of delivering on its promise to find the most tantalizing kinds of worlds. What makes this planet so compelling begins with its serene environment. TOI 700D orbits an M-dwarf star located just over 100 light-years away in the constellation Dorado. While many red dwarfs are notorious for their violent outbursts of radiation, this particular star is remarkably quiet and well-behaved, showing no evidence of the devastating flares that plague systems like Proxima-Centauri. This stellar calmness is a gift to any potential life on its planets, as it allows for a stable climate and dramatically increases the chances that an atmosphere could persist over billions of years without being eroded away by relentless stellar winds. A year on this world lasts 37 Earth days, a leisurely orbit that places it squarely in the star's habitable zone, where models suggest surface temperatures could be just right for liquid water. The TOI 700 system is a fascinating family of worlds in its own right. Astronomers have confirmed 3 planets orbiting the star. The innermost, TOI 700b, is almost exactly Earth-size but orbits too close to be habitable. TOI 700c is a larger, gaseous mini-Neptune that sits between planet B and our prime target. Then there is TOI 700d, the outermost known sibling and the crown jewel of the system, a rocky planet with a radius just over 1.1 times that of Earth. Its position and size make it a prime analog to our own world, a canvas upon which scientists can paint detailed models of potential climates and environments. And those models reveal a planet of fascinating possibilities, because it is likely tidally locked, with one side always facing the star and the other in perpetual darkness. Researchers have used sophisticated climate simulations to predict what conditions might be like. One compelling scenario suggests TOI 700d could be a water world, completely shrouded by a deep global ocean, with a thick carbon dioxide-rich atmosphere creating a strong greenhouse effect to distribute heat toward the dark side. Another simulation paints a very different picture, a world with a vast eye-shaped cloud bank permanently fixed on the star-facing side, reflecting just enough light to keep the dayside temperate while weather patterns vary warmth to the cooler regions. This cloud structure could create a surprisingly habitable environment across much of the planet. The true power of TOI 700D's discovery lies in what it represents for the future of astronomy. TESS was built to find planets like this Earth-sized worlds around bright, nearby stars precisely so they could be followed up by larger telescopes. Its identification opened the floodgates. Since its discovery, TESS has found thousands more planetary candidates, but TOI 700D remains a flagship target. Its parent star's brightness and stability, combined with the planet's favorable transit, make it one of the best candidates in the entire sky for atmospheric characterization with the James Webb Space Telescope. We are on the cusp of being able to peer into the air of this distant world, searching for the chemical signatures that could tell us if it is a humid, ocean-covered globe or a world with a more familiar mix of land and sea. It stands as a testament to a new, systematic era of discovery, where we are moving beyond simply finding planets to deeply understanding them, one bright, nearby star at a time. Sometimes the most incredible discoveries are hiding in plain sight, waiting for a second look and a human touch to bring them into the light. That is precisely the story of our 10th world, Kepler 1649c, an exoplanet that managed to evade automated algorithms only to be found by the keen eyes of amateur astronomers. This Earth-sized gem, located 300 light-years away, offers one of the most compelling combinations of features we've ever seen. A planet almost exactly our size, orbiting perfectly within its star's habitable zone. Its discovery is a powerful reminder that in our age of advanced artificial intelligence, human curiosity and pattern recognition remain irreplaceable tools in the cosmic detective's kit. The tale begins with the Kepler Space Telescope's monumental dataset. After the spacecraft's primary mission ended, a powerful algorithm named RoboVator was tasked with sifting through thousands of potential planetary signals, classifying them as either confirmed planets or false positives. In its ruthless efficiency, RoboVator examined the data from the star Kepler 1649 and dismissed one particular signal as nothing more than noise or a statistical glitch. The potential planet was cast aside, lost in a digital graveyard of rejected candidates. It wasn't until a team of volunteers with the Kepler False Positive Working Group decided to manually review these computer rejects that the error was caught. These citizen scientists, combing through the data for fun and for science, spotted the telltale rhythmic dips in starlight that the algorithm had missed. Their finding was then passed to professional astronomers who confirmed it. A rocky world just 1.06 times the size of Earth was real. This world's appeal lies in its striking similarity to our own. Its radius is virtually identical to Earth's, making it one of the closest twins we have found in terms of physical dimensions. But the similarities get even better. Kepler 1649c orbits its cool, red M-dwarf star squarely in the middle of the habitable zone. The amount of stellar energy it receives from its sun is calculated to be about 75% of the energy Earth gets from our sun. This places it in a remarkably temperate position, suggesting that if it possesses an Earth-like atmosphere, its average surface temperature could be very similar to our own planet's. The combination of Earth-like size and Earth-like temperature is the holy grail for exoplanet hunters, and Kepler 1649c is one of the few worlds to check both of those critical boxes. Adding another layer of intrigue to this system is the presence of a planetary sibling. Kepler 1649c is not alone. It shares its star with at least one other confirmed planet, a rocky world closer in. The two planets are locked in an orbital resonance, a delicate gravitational dance where for every 4 orbits the inner planet completes. Kepler 1649c completes almost exactly 9. This rhythmic, stable relationship hints at a system that has settled into a long-term, orderly configuration, which is favorable for the development of life over astronomical timescales. The star itself, while a red dwarf, appears to be relatively quiet compared to some of its flaring counterparts, further boosting the prospects for a stable climate. The legacy of Kepler 1649c extends far beyond its promising characteristics. Its discovery story has fundamentally changed how astronomers approach data analysis. It served as a crucial lesson that our automated tools, while incredibly powerful, are not infallible and can sometimes be too strict in their criteria, throwing out the cosmic baby with the bathwater. This event prompted scientists to go back and reanalyze the entire Kepler dataset with more nuanced algorithms and increased human oversight, a process that has likely unveiled other hidden gems waiting to be found. Kepler 1649c stands as a testament to the power of collaboration between humans and machines, and a symbol of hope that even in a universe of vast data, there is still a vital role for human intuition and perseverance in the search for our celestial neighbors. Venturing just 22 light-years from Earth, we find a world that offers a glimpse into the incredible diversity of planetary systems. GJ 667cc is a super-Earth that doesn't just orbit a single star. It exists within a complex gravitational dance in a triple star system, making its environment one of the most unusual we've yet discovered. With a mass about 3.7 times that of Earth, this planet falls squarely into the category of a super-Earth, large enough to likely retain a substantial atmosphere yet small enough to potentially be a rocky world. Its most captivating feature is its location, sitting firmly within the habitable zone of its primary star, a red dwarf known as GJ 667c. This parent star is itself part of a wider celestial family. It orbits a pair of larger, orange dwarf stars that are locked in their own tight binary embrace. From the surface of GJ 667cc, the view would be nothing short of spectacular. The primary red dwarf sun would dominate the sky, but the two other stars would also be visible, appearing as intensely bright points of light, perhaps even as brilliant as our own full moon, casting additional shadows and creating a complex cycle of daylight and twilight. While these companion stars are too far away to provide significant warmth, their gravitational influence and their light would profoundly shape the environment and rhythm of this distant world. Like many planets orbiting cool red dwarfs, GJ 667cc is almost certainly tidally locked, meaning one hemisphere is permanently baked in daylight while the other is frozen in an endless starlit night. This would seem to create a world of extreme opposites, but the potential for habitability is far from lost. A thick atmosphere could act as a global heat distributor, circulating warm air from the day side to the night side and preventing the atmosphere from freezing solid on the dark hemisphere. This could create a sprawling temperate zone along the terminator line, the border between light and dark, where conditions might be just right for liquid water to exist. The planet receives slightly less light from its star than Earth does from the Sun, but because much of that light is in the infrared spectrum, which is more efficient at heating, it could actually enjoy similar surface temperatures to our own planet, assuming it has a comparable atmosphere. The existence of a potentially habitable world in such a complex system is a revelation for astronomers. It demonstrates that planetary formation is not only possible, but can succeed in environments we once considered too chaotic and unstable for stable orbits. The presence of multiple stars does not automatically preclude the possibility of life. It simply creates a different set of conditions for it to arise. GJ 667cc expands our understanding of the galactic habitable zone, showing that promising worlds can exist in a much wider variety of stellar neighborhoods than we ever imagined. This super-Earth stands as a powerful symbol of nature's ingenuity, proving that even in a system with 3 suns, the basic ingredients for life, a rocky world with the potential for liquid water, can still come together. Now we come to a world that feels hauntingly familiar, a planet that has earned the poignant nickname Earth's cousin. Located 1,400 light-years away in the constellation Cygnus, Kepler 452b represents a profound milestone in our search for another Earth. While we have explored super-Earths and tantalizing ocean worlds, this planet stands out for a singular reason. It is the first near-Earth-size world discovered orbiting in the habitable zone of a star that is strikingly similar to our own Sun. This isn't a chaotic red dwarf system. This is a place that from a distance looks and feels almost like home. The statistics of Kepler 452b are what grant it such a special status. Its radius is about 1.6 times that of Earth. This places it in a category larger than a true twin but smaller than most known super-Earths, making it a very close relative. Even more compelling is its orbit. A year on this distant world lasts 385 days, just 20 days longer than our own annual journey around the Sun. This means it occupies a position in its stellar system that is almost a mirror image of Earth's place in our solar system, receiving a very similar amount of energy from its parent star. The combination of its Earth-like orbit and its Sun-like star creates the most convincing analog to our own planet-star relationship that we have found to date. The star itself, Kepler 452, is the true anchor of this compelling similarity. It is classified as a G-type star just like our Sun. It has nearly the same temperature and mass, and its radius is only 10% larger. If you were standing on the surface of its orbiting planet, the Sun in the sky would look almost indistinguishable from our own. However, this star holds a key difference that adds a deep, almost philosophical dimension to this discovery. Kepler 452 is significantly older than our Sun, by about 1.5 billion years. This advanced age is a double-edged sword. On one hand, it means this system has had an extra 50% more time than our solar system for life to emerge, evolve, and potentially develop complexity. It presents the breathtaking possibility of a biosphere far more ancient and advanced than anything on Earth. On the other hand, this great age also hints at a possible future for our own world. As stars like our Sun age, they gradually grow hotter and brighter. Models suggest that Kepler 452 is now about 20% brighter than it was when it first formed. This means the planet Kepler 452b is currently experiencing the kind of intensified solar energy that Earth will face in a distant future, a preview of the greenhouse warming that will one day render our own planet uninhabitable. This leads to a critical question known as the Fulton Gap, an observed phenomenon where few planets are found with sizes between 1.5 and 2 times Earth's radius. One theory is that planets of this size, when subjected to increasing heat from their aging stars, can undergo a runaway greenhouse effect. Their atmospheres, once rich with water vapor, could be utterly evaporated into space, leaving behind a desiccated, Venus-like world. This is the central mystery and the poignant beauty of Kepler 452b. Is it a verdant, life-bearing world that has enjoyed 6 billion years of stable evolution, a testament to longevity and cosmic fortune? Or is it a cautionary tale, a preview of Earth's ultimate fate, a once habitable world that has been slowly cooked by its own Sun into a barren wasteland? We simply do not know yet. Its distance makes detailed atmospheric study incredibly challenging with our current technology. But what it provides is an invaluable data point, a glimpse into the long-term evolution of a system so much like our own. It is a cosmic mirror reflecting both our past and our potential future, reminding us that even the most Earth-like worlds are subject to the relentless march of cosmic time. Now we turn our attention to a world so tantalizingly close that it practically beckons us for a closer look. just 14 light-years from Earth, a cosmic stone's throw in astronomical terms, orbits Wolf 1061c, a super-Earth that stands as one of our very nearest neighbors in the habitable zone. This proximity alone makes it an irresistible target, a world that future generations of telescopes and perhaps even interstellar probes might one day study in breathtaking detail. Imagine a planet with a mass about 4 times that of our own, a substantial world that almost certainly possesses the gravity necessary to hold onto a life-sustaining atmosphere. It resides comfortably within the habitable zone of its parent star, Wolf 1061, a calm and stable red dwarf, receiving just enough stellar energy to potentially allow liquid water to flow on its surface. Given its orbit around a cool, dim star, Wolf 1061c is almost certainly tidally locked. This creates a planet of profound extremes, with one hemisphere perpetually scorched by the unwavering light of its sun, and the other plunged into an eternal, deep freeze night. But within this stark division lies a realm of fascinating possibility. The most likely haven for life would be within the planet's twilight ring, the thin band of territory that separates day from night. Here, temperatures could be moderate, a perpetual golden hour where the star hangs permanently on the horizon, casting long shadows across a landscape that might host liquid water. A sufficiently thick atmosphere could act as a planetary life support system, circulating heat from the blazing day side to the frigid night side, potentially creating a much broader temperate zone than we might initially assume. The true, enduring value of Wolf 1061c lies not just in its potential habitability, but in its location. 14 light-years is an immense distance for human travel, but for the power of our telescopes, it is an ideal laboratory. The closer a potentially habitable world is to us, the brighter it appears and the easier it is to study. When scientists aim to use techniques like direct imaging, where we might one day blot out the star's glare to actually see the faint point of light of the planet itself, or sophisticated spectroscopy to analyze its atmosphere, every light-year of distance matters tremendously. Wolf 1061c is positioned perfectly for this next great leap in observation. It is a prime candidate for the upcoming extremely large telescopes, like the giant Magellan Telescope and the 30-meter telescope, which will have the resolution and light-gathering power to begin probing its atmosphere for signs of water vapor, oxygen, or methane. Furthermore, the entire Wolf 1061 system exhibits a remarkable gravitational stability that adds to its appeal. It is home to at least 3 known planets, with Wolf 1061c sitting in the middle of the pack. The outer planet is a cold, distant world, while the inner one orbits too close to the star to be habitable. This orderly arrangement suggests a system that has settled into a long-term, predictable dance, a stable environment that is crucial for life to have the time to emerge and evolve over billions of years. The parent star itself, while a red dwarf, is notably quiet, showing fewer of the violent flares that can sterilize nearby planets, which greatly enhances the prospects for any atmosphere to persist. Wolf 1061c represents the incredible value of our local cosmic neighborhood. It is a nearby test case for the conditions of red dwarf habitability, a world we can watch and study for decades to come as our technology races to catch up with our ambition to understand it. Leaving the familiar confines of our immediate stellar neighborhood, we now set our sights on a star system that offers a fascinating glimpse into the potential for super-sized Earths. 42 light-years away, the orange K-type star HD 40307 plays host to a family of at least 6 known planets, but one of them stands out as a world of exceptional promise. HD 40307G is a super-Earth of formidable proportions, with a minimum mass nearly 7 times greater than our own planet. This places it in a category that doesn't exist in our solar system, a massive terrestrial world that could have a landscape of vast mountain ranges and deep chasms on a scale we can scarcely imagine. Despite its heft, what truly captivates astronomers is its position, orbiting comfortably within its star's habitable zone, a region where temperatures could allow for the existence of liquid water, the essential ingredient for life as we know it. The characteristics of its parent star add a compelling layer to this planet's story. Unlike the turbulent red dwarfs we've encountered, HD 40307 is a K-type orange dwarf. These stars are renowned for their stability and longevity, burning their fuel at a slower, more consistent rate than our own Sun. They offer a serene and steady source of energy, providing any orbiting planets with a calm stellar environment free from the violent flares that could strip away atmospheres and scupper the chances for life. This stability is a gift, offering a potentially habitable world a multi-billion-year window of opportunity for biology to emerge and evolve without the constant threat of stellar tantrums. One of the most intriguing features of HD 40307G is its orbit. Unlike many planets tightly bound to dim stars, this world is far enough from its sun that it is likely not tidally locked. This means it could rotate on its axis in a way that creates a regular day-night cycle, much like Earth's. Even more exciting is the possibility that its rotational axis could be tilted. Axial tilt is the engine that drives seasons on our planet, and if HD 40307G shares this characteristic, it could experience a cyclical variation in climate, warm summers, cooler winters, and everything in between. Seasonal changes are not just a pleasant feature, they can drive ocean currents, mix atmospheric gases, and promote biological diversity by creating a wider range of ecological niches for life to exploit. The immense mass of this super-Earth is a double-edged sword. On one hand, such powerful gravity would be exceptionally effective at holding onto a thick, substantial atmosphere. This atmospheric blanket would be crucial for regulating surface temperature, shielding the planet from cosmic radiation, and providing the pressure necessary for liquid water to pool on the surface. It could create a potent greenhouse effect, potentially warming the planet enough to be habitable even if it receives slightly less energy from its star than Earth does. On the other hand, that same intense gravity presents challenges. The surface would feel much heavier, walking would be a laborious task, and any life forms would need to be robustly built to withstand the constant pressure. The atmosphere itself could be incredibly dense, creating surface pressures far greater than we experience, which would affect everything from the boiling point of water to the very chemistry of life. This leads us to a profound shift in perspective. When we search for life, we often seek a second Earth, but worlds like HD 40307G force us to broaden our imagination. A massive rocky planet isn't merely a scaled-up version of our home. It is an entirely different class of world with its own unique rules and possibilities. Life here would evolve under dramatically different physical constraints. It might favor low-lying, sturdy organisms. Biochemical processes could operate at different rates. The very sky might be a different color due to how light scatters in a denser atmosphere. HD 40307G challenges our Earth-centric view of habitability, suggesting that the most common abodes for life in the galaxy might not be petite twins of our world, but these colossal super-Earths, planets that offer a bigger canvas, a thicker protective shield, and a gravitational embrace strong enough to nurture life in ways we are only beginning to conceive. While many of the worlds we've explored represent recent leaps in discovery, we now turn to a planet that holds a special place in the history of exoplanet science, a world that, when it was confirmed in 2011, sent ripples of excitement through the global scientific community and fundamentally reshaped our cosmic perspective. Kepler 22b was not just another entry in a growing catalogue. It was the Kepler Space Telescope's very first confirmed planet found orbiting comfortably within the habitable zone of a Sun-like star. This discovery was a watershed moment, a powerful validation of the mission's core purpose, and a declaration that the age of hunting for Earth-like worlds had truly begun. Before Kepler 22b, the idea of finding a planet in that Goldilocks region, where temperatures might allow for liquid water around a star similar to our Sun, was largely theoretical. The handful of habitable zone planets known at the time orbited pulsars or were gas giants, fascinating in their own right but not analogues for Earth. Kepler 22b changed that narrative completely. Here was a world 600 light-years away in the constellation Cygnus, orbiting a G-type star almost identical to our own Sun, situated perfectly in the sweet spot where water could pool on its surface. The data was clear and undeniable, and it opened a floodgate of possibility. The planet itself is a super-Earth with a radius about 2.4 times that of our home world. This size places it in a fascinating category, larger than the rocky planets we know but smaller than the ice giants Uranus and Neptune. This immediately sparked a vibrant debate that continues to this day about the true nature of such worlds. Is Kepler 22b a massive rocky planet, a so-called mega-Earth with a solid surface and perhaps a formidable landscape of vast continents and deep oceans? Or is it a mini-Neptune, a world with a small rocky core enveloped by a deep, thick atmosphere of hydrogen and helium, lacking any definable surface at all? This question is central to its potential for life. A rocky super-Earth could offer a familiar, if larger, stage for biology. A gaseous mini-Neptune, with its crushing pressures and lack of a surface, would present a far more alien and challenging environment. A year on this distant world lasts 290 Earth days, an orbital period not too dissimilar from our own. Its sun, Kepler 22, provides a reassuringly familiar source of energy, though it is slightly smaller and cooler than our Sun. If you could stand on its surface, assuming it has one, the Sun in the sky would look remarkably similar to our own. The amount of stellar energy it receives is about 25% less than what Earth gets, but if it possesses an atmosphere with a moderate greenhouse effect, similar to our own, average surface temperatures could be a very comfortable 22 degrees Celsius, a pleasant spring day on Earth. This combination of a Sun-like star and a temperate orbital position made Kepler 22b the most Earth-like world known at the time of its discovery. But the true, enduring legacy of Kepler 22b lies not in its specific characteristics, which we are still working to pin down, but in the profound shift it triggered in our understanding of the cosmos. Its discovery was a powerful piece of statistical evidence. The Kepler telescope found it so early in its mission, by staring at such a tiny patch of sky, that it implied something extraordinary. Planets in the habitable zones of their stars were not rare, fluky occurrences. They were common. The galaxy, it seemed, was teeming with potential real estate for life. This single data point fueled a new optimism, suggesting that the Milky Way could contain not just a handful, but billions of worlds with conditions suitable for liquid water. It transformed the search for life from a question of if to a question of how many, galvanizing public imagination and securing support for the next generation of telescopes designed to study these worlds in greater detail. Kepler 22b was the proof of concept, the first definitive sign that we were on the right track in our quest to find another living world, and it forever expanded our vision of what is possible in the universe around us. While many nearby red dwarfs seem to wage a constant war of radiation against their planets, there exists a much gentler neighbor, a star that offers a far more serene promise for life. Just 11 light-years from Earth, Ross 128 is a red dwarf that stands in stark contrast to the violent tantrums of Proxima-Centauri. It is an old, quiet, and remarkably stable star, and orbiting peacefully within its habitable zone is Ross 128b, an Earth-sized world that has quickly become one of the most promising candidates for potential habitability in our entire celestial neighborhood. What sets this planet apart isn't just its size or its position, but the profound calm of its sun, a characteristic that might make all the difference between a sterilized rock and a living world. The parent star is the true hero of this story. Ross 128 is what astronomers call an inactive flare star. This means it has likely passed through its tumultuous youth billions of years ago and has now settled into a long, quiet retirement. While Proxima-Centauri frequently unleashes devastating flares that can bombard nearby planets with enough X-ray and ultraviolet radiation to strip away atmospheres and scorch surfaces, Ross 128 does none of that. Its luminosity remains steady, offering its planetary family a constant, gentle flow of energy rather than a series of violent outbursts. This stability is the greatest gift a star can give to a potentially habitable planet. It allows for the possibility that an atmosphere once formed could persist for billions of years, protecting the surface and nurturing the delicate chemical reactions that could lead to life. This serene stellar environment bathes the planet Ross 128b in a dim, reddish light. The planet orbits 20 times closer to its star than Earth does to the Sun, completing a full revolution in just under 10 Earth days. This close proximity almost certainly means the planet is tidally locked, with one side in perpetual daylight and the other in endless night. However, the extreme temperature difference this creates is not necessarily a death sentence. A reasonably thick atmosphere would work to distribute heat from the hot day side to the cold night side, potentially creating a wide, temperate band along the terminator line where conditions could be just right for liquid water. The planet receives about 38% more stellar radiation than Earth does, but because much of that energy is in the form of infrared light, the actual heating effect is very similar to what our own planet experiences. The combination of these factors, an Earth-like size, a location in the habitable zone, and an incredibly stable, quiet star makes Ross 128b a premier target in the search for biosignatures. Its proximity to us is the final, crucial piece of the puzzle. At just 11 light-years away, it is one of our closest potentially habitable neighbors. This makes it an ideal candidate for detailed study with the next generation of giant ground-based telescopes, like the Extremely Large Telescope and future space observatories. These powerful instruments will attempt to directly analyze the chemical composition of its atmosphere by studying the starlight that filters through it. The hope is to detect the telltale signs of a living world, such as the simultaneous presence of oxygen and methane, gases that typically cancel each other out unless they are being continuously replenished by biological processes. Ross 128b presents a compelling vision of cosmic habitability that doesn't require finding an exact replica of Earth. Instead, it suggests that longevity and stability might be the most valuable currencies in the galaxy. A planet orbiting a calm, ancient star has been granted the one resource life needs most: time. Billions of years of uninterrupted, peaceful evolution could allow for biochemistry to proceed at a leisurely pace, potentially leading to a rich and complex biosphere. This world teaches us that in the search for life, we shouldn't just listen for the loudest signals. Sometimes the most promising whispers come from the quietest stars. Now we journey to a system that presents not just one, but two potential havens for life orbiting the same star, a celestial double offering that challenges our notions of how planetary families form. 1,200 light-years away, the star Kepler-62, an orange dwarf slightly smaller and cooler than our Sun, is the proud parent of a remarkable family of 5 known planets. While all are fascinating, 2 of its children, Kepler-62e and Kepler-62f, stand out as crown jewels, both orbiting serenely within their star's habitable zone. This makes the Kepler-62 system one of the most precious finds in the exoplanet catalog, a place where the conditions for life might have arisen not once but twice in the same stellar backyard. The two worlds are both classified as super-Earths, but they offer distinct and compelling profiles. Kepler-62e is the larger of the pair, with a radius about 1.6 times that of Earth. It orbits closer to the star, completing a revolution in 122 Earth days. Its sibling, Kepler-62f, is slightly smaller at 1.4 Earth radii and occupies a more distant, cooler orbit, taking just over 267 days to complete a year. Their placement is a masterclass in the architecture of habitable zones. 62e sits on the inner, warmer edge, while 62f resides on the outer, cooler boundary. This creates a fascinating spectrum of potential environments within the same system, a range of possibilities from a warm, tropical world to a cooler, more glacial one. What truly captivates scientists about both of these planets is their very low density. While their exact masses are challenging to pin down, their physical sizes combined with models of planetary formation strongly suggest that they are not dense, rocky worlds like our own. Instead, the leading hypothesis is that both Kepler-62e and Kepler-62f are water worlds. Imagine a planet where the entire surface is a single, global ocean, not dozens but hundreds of miles deep, covering any underlying rocky core entirely. There would be no continents, no mountains breaking the surface, just an endless, dark aquatic expanse. Beneath a thick, humid atmosphere, the pressure at the bottom of such an ocean would be unimaginable, creating exotic forms of ice, not cold, but hot and solid due to the immense force. The existence of two such worlds in one system expands our imagination for what a biosphere could look like. Life on Earth began in the oceans, and a water world would offer a virtually infinite volume for aquatic life to develop and evolve. Microorganisms could flourish near the sunlit surface, while deeper, mysterious ecosystems might thrive around hydrothermal vents on the ocean floor, powered by chemical energy rather than sunlight, just as they do in the deepest trenches of our own planet. The possibility of two separate, vast oceans in the same system, each on a different world, presents the breathtaking concept of independent origins of life within a single family of planets. This dual discovery fundamentally changes our understanding of planetary system formation. Before Kepler, we based our models on our own solar system, with a neat arrangement of small rocky worlds inward and gas giants outward, and only one planet clearly in the habitable zone. The Kepler-62 system shatters that template. It shows us that a single star can nurture multiple Earth-sized planets within its habitable zone, a configuration we once might have considered overcrowded or gravitationally unstable. This revelation suggests that compact, multi-planet systems with several promising worlds could be common around red and orange dwarf stars, which are themselves the most numerous stars in the galaxy. The Kepler-62 system is a powerful symbol of cosmic abundance, a hint that the universe might not be frugal with its gifts, but instead generously offers multiple chances for life to emerge around a single, nurturing sun. Traveling 36 light-years from Earth, we encounter a world that serves as a milestone from an earlier era of exoplanet discovery, a planet that helped define the very standards by which we judge potential habitability. HD 85512b is a super-Earth with a mass approximately 3.6 times that of our own planet, orbiting a K-type orange dwarf star. When it was first detected in 2011 by the HARPS instrument in Chile, its discovery generated significant excitement because it represented something new and profoundly promising. It was one of the very first planets ever found to be orbiting squarely within its star's so-called conservative habitable zone. This conservative definition is a stricter, more cautious estimate of where liquid water could exist, focusing on the conditions that would allow for an Earth-like atmosphere and climate, making any world within it an immediate candidate for further study. The planet's orbit is remarkably stable and circular, completing a full revolution around its star in just 58 Earth days. This places it relatively close to its Sun, but because that Sun is a cooler, dimmer K-type star, this proximity is precisely what lands it in the temperate habitable zone. The amount of stellar energy it receives is calculated to be just right about as much as Venus gets from our Sun, but crucially, scientists believe that with a cloud cover of around 50%, similar to Earth's average, its surface temperatures could be moderated into a comfortable, life-friendly range. This interplay between stellar flux and planetary albedo, or reflectivity, was a key part of the early optimism surrounding this world, suggesting that it had the fundamental ingredients for a stable climate. A major part of HD 85512b's appeal lies in the serene nature of its parent star. Unlike the volatile red dwarfs that dominate our list, this K-type star is exceptionally stable and mature, showing very little of the magnetic activity and flaring that can bombard nearby planets with harmful radiation. This stability is a gift to potential atmospheres and biospheres. It offers a calm, predictable environment where life could have had billions of years to emerge and evolve without the constant threat of being sterilized by a stellar outburst. The star's advanced age means this system is a quiet, well-ordered place, a stark contrast to the chaotic youth of many other systems we've explored. When it was discovered, HD 85512b stood out for its relatively low minimum mass for a super-Earth. This placed it firmly in the category of a potentially rocky world, rather than a gaseous mini-Neptune, which was a critical distinction at the time. Its discovery, alongside a handful of others, marked a turning point. It proved that the habitable zones of other stars were not empty. They were populated with worlds of substance that we could actually detect and begin to characterize with our ground-based telescopes. It moved the search for life from pure speculation into the realm of tangible, data-driven inquiry, providing a specific and exciting target for the next generation of observatories. While newer discoveries may have overshadowed it in terms of Earth similarity or proximity, HD 85512b remains an important historical marker, a testament to the rapid progress in our field and a reminder of the profound excitement that greeted each new world found in that celestial sweet spot. Amidst a cosmos teeming with red dwarf systems, we now turn our attention to a world that feels profoundly familiar, offering a glimpse into a different kind of planetary family. 3,000 light-years away, orbiting a star remarkably similar to our own Sun, is Kepler 1638b. This Earth-sized planet represents a significant and hard-won victory for astronomers, a discovery that required years of meticulous work to confirm its existence and its promising position. While many of the worlds on our list orbit small, cool stars, Kepler 1638b stands out because it reminds us that Sun-like stars also host potentially habitable, Earth-sized worlds, expanding the canvas upon which life could paint its story. The confirmation of this planet in 2017 was a testament to perseverance in modern astronomy. The initial detection came from the Kepler Space Telescope, which observed the telltale dimming of the star's light as the planet passed in front of it. But for a planet of this size orbiting a star so similar to our Sun, the signal was incredibly faint and could easily have been a false positive caused by a background star or instrumental noise. It took an extensive, multi-year campaign of follow-up observations using ground-based telescopes and sophisticated statistical analysis to rule out every other possible explanation. This painstaking process highlights a critical challenge in the search for another Earth. Finding a true twin is extraordinarily difficult. Planets around G-type stars like ours have longer orbital periods, meaning we have to wait years to observe multiple transits to confirm their existence, and their transits are shallower and less frequent, making the signals incredibly delicate to tease out from the data. What emerged from this rigorous verification is a profoundly enticing world. Kepler 1638b has a radius almost identical to Earth's, making it a true peer in terms of physical size. But its most captivating feature is its orbit. This planet completes a full journey around its Sun-like star in 259 days, a year only about 100 days shorter than our own. This orbital period places it squarely within the star's calculated habitable zone, that region where temperatures could allow for liquid water to exist on a rocky surface. The amount of stellar energy it receives is very similar to what Earth gets, suggesting that if it possesses an atmosphere with a composition akin to ours, its surface climate could be strikingly temperate and Earth-like. This discovery teaches us a vital lesson about the breathtaking diversity of planetary systems. Our own solar system, with its single habitable zone planet, is just one possible architectural blueprint. The Kepler 1638 system shows us that a Sun-like star can host a world with an Earth-like orbit and an Earth-like size, a combination we once might have assumed was rare. It proves that the ingredients for a familiar kind of habitability are not confined to the most common type of star, the red dwarf, but are also present around stars like our own. This expands the number of potential abodes for life in our galaxy exponentially, suggesting that while red dwarf systems may be numerous, there is also a vast array of solar analogues with their own Earth-sized planets waiting to be found. Kepler 1638b is a beacon of a more familiar potential future, a world that doesn't require us to imagine life under a perpetual red twilight or on a tidally locked globe, but allows us to dream of a planet with a yellow sun in its sky and a yearly rhythm not too different from our own. Returning to the stunning cosmic dance of the TRAPPIST-1 system, we find that the promise of this family of worlds extends far beyond the single planet we explored earlier. While TRAPPIST-1e rightfully commands attention, it is not alone in its potential. It shares the star's habitable zone with not one, but two, and arguably even three, other siblings planets D, F, and G. Each of these worlds occupies a different strategic position within that temperate band, creating a remarkable spectrum of possible environments and offering not just one, but multiple chances for life to have arisen in this single, extraordinary system. Planet D, the innermost of this habitable trio, sits on the warmer edge of the zone. It's a world that receives about 4 times more stellar energy than Mars, but only half of what Venus gets from our Sun. This places it in a fascinating, if perilous, position. It could be a temperate world, perhaps a touch warmer than Earth, with vast, shallow seas and a humid, thick atmosphere. Alternatively, if its atmosphere is too thin or it has lost too much water, it could be a scorching desert, a victim of a runaway greenhouse effect that boiled its oceans away long ago. Planet D represents the potential for a tropical, Venus-like past or present, a world where life would have to contend with intense heat and powerful weather systems. On the opposite, cooler end of the spectrum lies TRAPPIST-1g, the largest planet in the system. It orbits on the outer fringe of the habitable zone, receiving a similar amount of energy as the asteroid Ceres does in our solar system. At first glance, that might seem far too cold, but the rules change for a planet of its size. Its greater mass means it could easily hold onto a massive atmosphere, potentially rich in hydrogen or greenhouse gases like methane. This atmospheric blanket could act as a powerful insulator, trapping enough heat to maintain a vast global subsurface ocean beneath a thick icy crust, not unlike Jupiter's moon Europa, but on a much larger scale. TRAPPIST-1g could be a frozen world on the surface, hiding a dark, deep, and potentially life-filled abyss below. Occupying the middle ground between these two extremes is TRAPPIST-1f. This world is perhaps the most intriguing of the three after Planet E. It receives just a bit less stellar flux than Earth, positioning it perfectly for a climate that could be remarkably similar to our own, assuming it has a suitable atmosphere. It's a prime candidate for a true water world, potentially covered in a single globe-spanning ocean. Its size, slightly larger than Earth, gives it the gravity to hold onto a substantial atmosphere, which could efficiently distribute the star's warmth across its surface. If any planet in this system were to have conditions we would instantly recognize as Earth, like TRAPPIST-1F is a very strong contender. The true wonder of this system lies not just in the number of habitable zone planets, but in their breathtaking proximity to one another. The entire compact family of 7 worlds orbits their star at a distance smaller than the orbit of Mercury around our Sun. The planets are so close together that from the surface of one, the others would not be mere points of light but breathtaking celestial orbs, appearing larger than our own moon and showing visible disks and features in the sky. You could potentially see the cloud patterns of a neighboring world with the naked eye. This incredible compactness turns the entire system into a single, interconnected laboratory. The close quarters raise fascinating possibilities such as panspermia, the natural transfer of life between planets via meteorites blasted from one world's surface by an impact only to land on another. If life did emerge on just one of these worlds, it could have easily seeded all the others, meaning the TRAPPIST-1 system might not host several separate biospheres, but one single system-wide biota, an interconnected web of life spanning multiple planets. This stunning arrangement offers a vision of cosmic companionship unlike anything in our own solar system, a place where the search for life isn't confined to a single world but reverberates across an entire celestial neighborhood. But our journey is not only about looking forward or outward, it is also about looking back deep into the cosmic past to a world that has witnessed almost the entire history of the universe itself. Just 13 light-years away orbits Captain B, a super-Earth that offers a perspective on time so vast it is almost incomprehensible. This planet, at least 5 times more massive than our own, orbits within the habitable zone of Captain Star, a dim red dwarf that holds 2 extraordinary titles. It is one of the closest stars to our Sun, and it is ancient, a relic from the earliest days of the galaxy with an estimated age of 11 billion years. To grasp that timescale, consider this: when the first single-celled organisms were beginning to stir in Earth's primeval oceans, life on Captain B, if it exists, could have already been evolving for over 6 billion years. The star itself tells a story of cosmic violence and migration. Captain Star is a halo star, meaning it does not orbit within the Milky Way's neat disk like our Sun. Instead, it plunges on a long, elliptical path that takes it high above and far below the galactic plane. It also possesses one of the highest proper motions of any known star, meaning it appears to race across our sky at a startling speed. This frenetic motion is a clue to its incredible past. Astronomers believe it was not born in this lonely orbit but was instead flung here, a refugee ejected from a dwarf galaxy that was torn apart and consumed by the infant Milky Way in a dramatic act of galactic cannibalism. This stellar wreckage, this ancient survivor, is the sun that shines on Captain B. This profound antiquity is the most compelling feature of this distant world. An age of 11 billion years means this planet has had more than twice the time that Earth has existed for life to emerge, adapt, and evolve. On our world, it took roughly 4 billion years for simple life to give rise to a technological civilization. What might have arisen on a world with over 11 billion years of stable conditions within the habitable zone? The possibilities are staggering. Life there could be so advanced and so deeply integrated with its environment as to be unrecognizable to us. Its biochemistry might be built on entirely different foundations, having had eons to perfect itself. Or it could represent a sobering answer to the Fermi paradox, a cautionary tale that even with all the time in the universe, intelligent life might be an incredibly rare or fragile phenomenon, perhaps inevitably facing challenges that lead to its stagnation or demise. The environment of Captain B, however, is not without its challenges. It orbits a red dwarf and is therefore likely tidally locked, presenting the now familiar picture of a day side and a night side of extreme temperatures. Yet its great age works in its favor. The star has long since settled from its volatile youth into a stable, quiet maturity, offering a consistent energy source for billions of years. Furthermore, the planet's substantial mass gives it a strong gravitational grip, making it highly capable of holding onto a thick, protective atmosphere that could distribute heat and shield the surface. The potential for a vast, global ocean or a complex, weathered landscape is very real. Studying a world like Captain B is like opening a history book to the very first chapter of the galaxy. It forces us to ask fundamental questions about life's cosmic timeline. Did life emerge quickly in the young universe, or was it a slow, gradual process? If we were to find evidence of a biosphere on such an ancient world, it would suggest that life is not a late-blooming fluke, but a natural and almost immediate consequence of the right conditions, ready to spark into existence as soon as the universe cooled enough to allow it. Captain B is a frozen moment from a time before our sun even ignited, a living fossil of a world that has been orbiting, waiting, and perhaps nurturing life since the cosmos was in its infancy. Sometimes the most intriguing stories in science are not about definitive answers, but about the passionate debates that push our understanding forward. This brings us to the compelling and controversial case of GJ581g, a world whose very existence became a battleground of data and interpretation, reminding us that the path to discovery is rarely a straight line. Located a mere 20 light-years away in the constellation Libra, this potential planet was announced in 2010 by a team led by astronomer Stephen Vogt. The claim was staggering. They had found a world with a mass 3 to 4 times that of Earth, orbiting squarely in the middle of its star's habitable zone. This wasn't just another exoplanet. If confirmed, it would have been one of the first and most promising potentially habitable worlds ever found, and tantalizingly close to us. The star GJ581 is a quiet red dwarf already known to host a family of other planets. The discovery of planet G seemed to crown this system as a jewel in the crown of nearby stellar neighbors. The initial detection was made using the radial velocity method, which involves measuring the subtle wobble of a star caused by the gravitational tug of an orbiting planet. The team analyzed over 200 observations from the Hycean spectrometer in Hawaii, painstakingly teasing out the faint signal they attributed to this new world. Their data suggested a planet with an orbital period of just 37 days, but because the star is so cool and dim, this close orbit was precisely what placed it in the temperate habitable zone. The possibility emerged of a rocky world with the right conditions for liquid water, a super-Earth that could potentially hold onto a life-sustaining atmosphere. The announcement captured the public's imagination and was hailed as a monumental step in the search for another Earth. However, in science, every extraordinary claim undergoes intense scrutiny, and the story of GJ581g took a dramatic turn. Shortly after the announcement, another team working with a separate, extensive dataset from the HARP spectrograph in Chile reanalyzed the stellar wobbles. They could not confirm the signal for planet G. Their conclusion was that the wobble Vogt's team had detected was not caused by a planet, but was actually an artifact of the star's own activity. Red dwarfs are known to have star spots and magnetic cycles that can create rhythmic variations in their light, mimicking the gravitational tug of an orbiting planet. The scientific community found itself divided, with some groups publishing analyses that supported the planet's existence and others that refuted it. For years, the status of GJ581g remained in a state of frustrating uncertainty, listed in some catalogs as a confirmed planet and in others as a retracted false positive. This intense debate, while seemingly a setback, was actually a demonstration of the scientific process working exactly as it should. The controversy forced astronomers to develop more sophisticated methods for distinguishing between genuine planetary signals and stellar noise. It highlighted the critical importance of using multiple, independent datasets and instruments to verify a discovery. The tools and statistical techniques refined during this period have since become standard practice, making our planet hunting methods more robust and reliable than ever before. We learn to be more cautious, to demand more evidence, and to better understand the complex behavior of the stars we observe. The legacy of GJ581G is therefore not about a single world, but about the rigor of the search itself. Even if its existence is never definitively proven, this controversial candidate played a crucial role in advancing the field. It served as a high-profile test case that ultimately strengthened the protocols for future discoveries, ensuring that the next potentially habitable world announced will have undergone the most stringent verification process possible. It reminds us that every claimed discovery, whether later confirmed or denied, adds a valuable piece to the puzzle, teaching us how to ask better questions and sharpen our tools for the next, even more promising, world that awaits our gaze. Our exploration of promising worlds now brings us to a pair of distant cousins whose stories serve as a crucial lesson in cosmic context: Kepler 438b and Kepler 440b. These two exoplanets, discovered by the Kepler Space Telescope, initially generated tremendous excitement as they both appeared to be some of the most Earth-like worlds ever found, each orbiting comfortably within their star's habitable zone. Yet further study revealed that their potential for life is severely challenged by their stellar environments, reminding us that a planet's address in that golden region is just the beginning of the story, not the happy ending. Let's begin with Kepler 438b, a world that on paper seems almost ideal. Located about 640 light-years away, this planet is a true Earth analog with a radius only 12% larger than our own world. It orbits a red dwarf star and sits perfectly within the conservative habitable zone, receiving about 40% more stellar energy than Earth gets from our Sun. If it possessed an atmosphere similar to ours, its surface temperature could be remarkably temperate. In fact, when it was discovered, it briefly ranked as the exoplanet with the highest Earth similarity index, a measure of how closely its conditions mirror our own. It represented the dream, an Earth-sized world in an Earth-like orbit. But this dream world orbits a nightmare star. Kepler 438 is a profoundly active red dwarf given to frequent and terrifyingly powerful superflares. These are not the mild solar flares our Sun occasionally produces. They are cataclysmic eruptions that unleash torrents of X-ray and ultraviolet radiation, billions of times more energetic than anything in our solar system's history. Research indicates that Kepler 438b is likely bombarded by these superflares every few hundred days. The effect on any potential atmosphere would be devastating. Such repeated blasts would act like a cosmic blowtorch, relentlessly stripping away the planet's protective gaseous envelope and scouring its surface with lethal radiation. Even if life somehow managed to gain a foothold, it would be periodically sterilized, resetting the evolutionary clock again and again. This world teaches us that a planet's potential is inextricably linked to the temperament of its star. The calmest, most stable orbit is meaningless if the Sun itself is a raging inferno. In stark contrast to the fiery fate of its cousin, our second world, Kepler 440b, faces the opposite extreme, the deep freeze. This super-Earth, about 1.8 times the size of our planet, orbits a star over 850 light-years away. It, too, was found within its star's habitable zone, but it resides on the zone's outermost, coldest fringe. The amount of stellar energy it receives is minimal, only about 26% of what Earth enjoys. For this world to have any chance of hosting liquid water, it would need a very specific and perhaps unlikely atmospheric composition. The hope for Kepler 440b hinges on a powerful greenhouse effect. If the planet has managed to retain a very thick atmosphere, rich in greenhouse gases like carbon dioxide or methane, that atmospheric blanket could trap enough heat to raise surface temperatures to a level where water could remain liquid. It's a delicate balancing act. Without such an atmosphere, the planet would be a frozen, icy wasteland, far too cold for life as we know it. However, there's a catch. Kepler 440b is significantly more massive than Earth, and it orbits a K-type star. Its greater gravity might help it hold onto a thick atmosphere, but its position so far from the star's warmth makes the required greenhouse effect a tall order. This world exemplifies the concept of the cold start problem. Being on the outer edge of the habitable zone might be just as challenging as being too close, requiring a set of atmospheric conditions that may be difficult to achieve and maintain over billions of years. Together, the tales of Kepler 438b and Kepler 440b form a critical narrative in astrobiology. They move us beyond the simple, two-dimensional concept of a habitable zone, that band around a star where it's not too hot and not too cold. Their stories introduce essential third and fourth dimensions, stellar activity and atmospheric chemistry. A planet's true potential for life is a complex equation balancing the amount of energy it receives, the star's stability, the planet's ability to hold onto an atmosphere, and the specific composition of that atmosphere. These two worlds, one threatened by stellar fury and the other by cosmic chill, are not failures or disappointments. They are profound teachers. They force us to refine our models, to look deeper, and to understand that the universe rarely offers simplicity. The search for another living world demands that we appreciate the intricate and delicate dance between a planet and its star, where sometimes even a perfect position isn't quite enough. Now we turn to a red dwarf neighbor that combines the thrilling potential for life with the incredible accessibility that makes it a prime target for the next decade of discovery. Just 12.2 light-years from Earth, a cosmic stone's throw away, orbits Hycean b, a super-Earth that stands as one of our very best chances to finally answer the question of whether we are alone. This world, with a minimum mass about 3 times that of our own planet, circles its quiet parent star, Hycean star, squarely within the habitable zone. This location suggests surface temperatures could, in theory, allow for the existence of liquid water, that all-important ingredient for life as we know it. But what truly sets Hycean b apart from countless other exoplanets isn't just its promising position, it's the profound combination of its serene stellar environment and its tantalizing proximity to our own solar system. The character of its sun is the first reason for such great optimism. Hycean star is an M-type red dwarf, but it belongs to a much more tranquil class than the flare-prone monsters like Proxima-Centauri. It's classified as an inactive star, meaning it has long since passed through the violent tantrums of its youth and settled into a stable, quiet maturity. This is a star that provides a constant, gentle flow of energy rather than unpredictable and lethal bursts of X-ray and ultraviolet radiation. For any potential atmosphere on Hycean b, this stellar calmness is a gift. It means a protective blanket of gases could have persisted for billions of years, shielding the surface from cosmic rays and maintaining the pressure necessary for liquid water to pool and flow. This stability offers a multi-billion-year window for the intricate chemistry of life to begin, a luxury not afforded to planets orbiting more tempestuous stars. Given its orbit around a cool, dim star, Hycean b is almost certainly tidally locked. One hemisphere is perpetually bathed in the dim, reddish glow of its sun, while the other is frozen in an eternal, starless night. This creates a world of extreme contrasts, but it is far from a death sentence for habitability. The key, as with many such worlds, lies in the atmosphere. A reasonably thick atmosphere would act as a planetary life support system, circulating heat from the scorching day side to the frigid night side. This could create a vast temperate zone along the terminator line, the border between light and dark, where conditions might be just right for a biosphere to thrive. The planet receives 86% more stellar energy than Earth does, but because much of that energy is in the infrared spectrum, the actual heating effect could create very Earth-like temperatures if the atmosphere is similar to our own. The sheer mass of this super-Earth is its second great advantage. A planet 3 times heavier than Earth possesses a much stronger gravitational pull. This powerful gravity is exceptionally effective at holding onto a substantial atmosphere over astronomical timescales, preventing it from being stripped away by stellar winds or slowly leaking into space. It suggests a world that could have a deep and complex atmosphere, potentially rich with the chemical signatures we associate with life. However, this same gravity would make the surface a much heavier place. Walking would be a laborious task, and any life forms would need to be robustly built to withstand the constant pressure. The very sky might appear different due to how light scatters in a denser air, and weather patterns could be more intense and powerful than anything we experience on Earth. But the single most compelling feature of Hycean b is its proximity. 12.2 light-years may seem an immense distance, but in the vast scale of our galaxy, it is right next door. This closeness is what makes it, and other nearby systems like it, our best and most immediate hope for characterizing a habitable world. The closer a planet is to us, the brighter it appears to our telescopes. This brightness is the currency of detailed observation. For the next generation of colossal ground-based telescopes, like the extremely large telescope and the giant Magellan telescope, and for future space-based observatories, Hycean b is a prime target. Its proximity means these instruments will have a fighting chance to directly analyze the chemical composition of its atmosphere. The technique they will use is called transmission spectroscopy. When Hycean b transits in front of its star from our viewpoint, a tiny fraction of the starlight filters through the planet's atmosphere. By dissecting that filtered light into a spectrum, astronomers can read the unique fingerprints of the gases present. They will be searching for biosignatures, combinations of gases that are difficult to explain through geology alone. The simultaneous presence of oxygen and methane, for example, would be a powerful, though not definitive, indicator of biological activity, as these gases typically react with and destroy each other unless they are being continuously replenished. Finding evidence of water vapor would be another crucial piece of the puzzle. Hycean b is close enough that we may actually get these answers within our lifetimes. It represents the frontier of a new era, moving from simply discovering planets to truly understanding them, and in doing so, it offers us our most tangible near-term prospect of looking upon another living world. For our final destination on this tour of alien worlds, we travel to a place that perfectly embodies the current frontier of exoplanet science. A world that doesn't offer easy answers but instead challenges us to refine our very definitions of what makes a planet livable. 2,500 light-years away, orbiting a star similar to our own Sun, is Kepler 443b, a planet that sits at the very outer edge of its star's calculated habitable zone. This position places it in a cosmic gray area, a region of profound ambiguity where the classic label of habitable becomes less a definitive statement and more a complex question mark. The energy it receives from its star is minimal, only about 32% of what Earth gets, suggesting a world that would be intensely cold without some significant atmospheric intervention. To have any chance of hosting liquid water, this planet would require a very specific and perhaps unlikely combination of factors. A thick, dense atmosphere dominated by potent greenhouse gases like methane or carbon dioxide, acting as an insulating blanket to trap every precious bit of stellar warmth. This is the first layer of its mystery, a world that is technically in the right neighborhood, but one that would need to engineer its own private spring through atmospheric chemistry to avoid being a permanently frozen ice ball. The intrigue deepens when we consider what this world is actually made of. With a radius measured at 2.33 times that of Earth, Kepler 443b falls into a category that has become a central puzzle in exoplanet science, the Fulton Gap. This is an observed scarcity of planets with sizes between 1.5 and 2 times Earth's radius. One leading theory for this gap is that planets that form around this size often can't hold onto their rocky composition. Instead, they accumulate such massive amounts of hydrogen and helium during their formation that they balloon into something entirely different, mini-Neptunes. These are not solid, terrestrial worlds with familiar surfaces, but gaseous envelopes surrounding a much smaller rocky core. For Kepler 443b, its size makes it far more likely to be one of these mini-Neptunes than a super-Earth. This distinction is absolutely critical. A mini-Neptune has no solid surface to speak of. Any potential ocean would not be a body of water resting on rock, but a vast, deep layer of supercritical fluid water thousands of miles deep, seamlessly blending into a thick, crushing atmosphere above and a high-pressure ice mantle below. In such an environment, the very chemistry of life as we understand it would be fundamentally altered, operating under pressures and conditions we can scarcely replicate in a laboratory. Yet, it is precisely this ambiguity that makes worlds like Kepler 443b so incredibly valuable to astronomers. They are not disappointments in the search for another Earth. They are essential boundary markers that help us chart the entire map of planetary possibility. By studying these borderline cases, planets on the edge of the habitable zone and on the edge of the rocky/gaseous divide, we are forced to move beyond our Earth-centric biases. We are compelled to ask more nuanced questions. How wide can the habitable zone truly stretch with different atmospheric compositions? Could life, in some form we haven't yet imagined, originate and persist not on a rocky surface, but in the upper cloud layers of a gaseous world, floating in a temperate band of atmosphere? Kepler 443b pushes us to consider that the classic recipe for habitability, a rocky planet with liquid water on its surface, might be just one page in a vast cosmic cookbook. It represents the exciting, ongoing process of science not as a set of fixed answers, but as a continuous refinement of our models. Each new world we discover, especially the complex and puzzling ones, adds a new data point, sharpening our tools and deepening our understanding of where and how life might find a way in this astonishingly diverse universe. From our next-door neighbor Proxima-Centauri-b to the ancient, time-worn Captain b 11 billion light-years away, this journey across 25 alien worlds has revealed a universe of breathtaking diversity and possibility. We have explored Earth-sized twins like Kepler 1638b orbiting Sun-like stars, and massive super-Earths like LHS 1140b that might be entirely shrouded in global oceans. We have seen worlds bathed in the perpetual twilight of quiet red dwarfs like Ross 128b, and others orbiting in the complex gravitational dance of triple-star systems like GJ 667cc. Some, like those in the TRAPPIST-1 system, offer not one but multiple chances for life around a single star, while others, like the Hycean world K218b, challenge our very definition of a habitable environment by suggesting life could thrive in the deep, dark oceans of a mini-Neptune. Each of these extraordinary places, from the scorching inner edge to the frozen outer fringe of their habitable zones, has rewritten the cosmic rulebook, teaching us that potential life is not limited to a single, Earth-like template, but could flourish in a stunning variety of forms and environments we are only beginning to imagine. The true revelation here is not just the existence of these worlds, but the profound expansion of what we now call the habitable zone. It is no longer a simple, narrow band where conditions must perfectly mirror our own. Instead, we have discovered it is a dynamic and multifaceted concept, broadened by the potential for thick greenhouse atmospheres on frozen worlds, subterranean oceans warmed by tidal forces on icy moons, and even life floating in the temperate cloud layers of gaseous planets. This new understanding means the number of potential abodes for life in our galaxy has grown exponentially, transforming the Milky Way from a vast, empty ocean into an archipelago of billions of islands, each with its own unique story and potential. Our ability to read these stories is on the verge of a quantum leap. The James Webb Space Telescope is already peering into the atmospheres of worlds like TRAPPIST-1e, searching for the chemical fingerprints of water vapor, oxygen, methane, and other potential biosignatures. But this is only the beginning. The next generation of colossal ground-based observatories, like the extremely large telescope and the 30-meter telescope, will have the power to directly image the faint light of exoplanets themselves, potentially mapping their surface features and weather patterns. And future missions like NASA's Habitable Worlds Observatory will be designed with one primary goal: to find conclusive evidence of life on a planet beyond our solar system by analyzing the light reflected from its atmosphere for signs of biological activity. This search leads us to a question far greater than mere astronomy. If we were to find that second genesis, that independent spark of life on any one of these 25 worlds, it would fundamentally alter our understanding of reality. It would mean that the universe is not just a beautiful, barren expanse of matter and energy, but a place teeming with biology. It would tell us that life is not a miraculous fluke confined to our pale blue dot, but a natural and common outcome of cosmic evolution. The philosophical and theological implications are staggering, forcing us to reconsider our place in the cosmos and our responsibility as the only known life form capable of seeking out others. This incredible journey of discovery belongs to all of us. It is a testament to our innate curiosity and our relentless drive to understand the universe and our place within it. So we want to hear from you. After exploring these 25 incredible worlds, from the fiery trials of Kepler 438b to the serene promise of Hycean b, which one captured your imagination the most? Do you dream of the twin worlds of Teegardens-star, basking in the light of their ancient sun? Or does the mysterious Hycean world K218b, with its potential signs of biological activity, fill you with the most wonder? Share your thoughts in the comments below and let us know which of these alien worlds you would most want to see revealed by the next generation of telescopes. The universe is vast, mysterious, and waiting for us to explore.